Let us go to the fourth problem now. So the set G is having four elements, 1, minus 1, I and minus I. And I have to show that this set forms a group with respect to usual complex multiplication. So I hope you know that I is nothing but our standard square root of minus 1. So now if I look at this set and if I try to look at the closure, you know, as usual I will do the same thing. I will write the four elements and prepare a table of this and show that all the entries in the table are again either 1, minus 1, I or minus I. So I'm going to multiply them. So 1 into 1 is 1, minus 1, I into 1 is 1, I, and 1 into minus I is minus I. This is again I'm going to multiply minus 1 to all the elements, minus 1, 1, minus I. When I multiply I to all of these elements, I will get I minus I. I into I is I square, which is I square is minus 1. I into minus I is minus of I square. Minus of I square is minus of minus 1. So that is 1. When I multiply minus I to all these elements, minus I multiplied by 1 is minus I. Minus I multiplied by minus 1 is I. I into I square, I into I is minus 1, so it will get 1. And minus I into minus I is I square, which is again minus 1. So all the entries are in the table. If I take A any element here and if I take B any element here, then we see that A into B is again coming up to be either 1, minus 1, I or minus I. So the closure gets completed over here. So we have verified the closure. Second is associativity. We will say that associativity holds because associativity holds in set of complex numbers. So associativity holds. We can check this. Third is identity. So do I see any element here in this set which I multiply with any other element, I will get the same element back. So A into E should be again equal to the same A. So this element is clearly identity is 1. So this 1 is the identity of my group. And the last part is inverse. I will take all the elements and I will check whether the inverses are there. So if I take element and if I take the inverse, A into B should be equal to identity. If that is the case, I will say that B is inverse of A. So the elements are 1, minus 1, I, minus I. So I will go back in the table, square all the identities, square these are the identities. So 1 into 1 is 1, so the inverse of 1 is 1. This says that minus 1 into minus 1 is 1, so inverse of minus 1 is minus 1. This is saying that I into minus I is 1. This means that inverse of I is minus I. And last is minus I into I is 1, so this means inverse of minus I is I. So all our elements have inverses and therefore we have verified all the four properties: closure, associativity, existence of identity and existence of inverse. So this means that G, which is 1 minus 1, I minus I, is a group. So this finishes the fourth problem.